My guest today is Dr. Julio Guerrero, who is CEO and founder of Cambridge Research and Technology, which provides consulting services and actionable innovations in engineering and scientific fields at any stage of product development. Industries in which he has focused lately include energy and biomedical, with concentrations in most domains inside mechanical, electronics, and civil engineering. Welcome, Julio.
Thank you very much, Jill.
Yeah, thanks for doing this. I used to be an engineer in my early life. I don't do much in engineering anymore. So I'm very keen on hearing more about what Cambridge Research and Technology does. But I want to put that in the context of some of your major focus areas. And one of them is energy. And before we get into the details of this, Julio, could you talk very quickly about what the company does?
Yes. So it's a consulting company. We operate mostly from Cambridge, Massachusetts, and we offer our clients a team that complements them through any phase of the process development, that TRL from 1 to 7. And the three main activities that we focus on are engineering and science, business development, and strategy. And in strategy, again, we focus on the strategic planning related to the science and engineering and innovation. And as you mentioned before, the three areas in which we have focused most lately is energy, biomedical, and civil. Most of our clients get the benefit that the IP that we develop during our projects, most of our clients can keep the IP.
So the client keeps IP in your projects?
Yes. Most, yeah.
So under energy, you have multiple areas here that you have been working on: green energy, off-grid energy sources, innovative residential geothermal. So I want to talk a bit about green energy. And I mean, there's a lot of attention here, a lot of interest and excitement here with the impending climatic catastrophe that we are expecting. And there are a lot of alternatives. I mean, there have been a lot of alternatives: solar, wind, hydrogen, so on and so forth. So what is sort of the status quo? Where are we now in terms of alternative sources in green energy?
Right. So I will start with the last one, with hydrogen. We have had some projects with one of our clients, is one of the top 4 players on the design and manufacturing of electrolyzers. I would say that is moving very quickly, but there are some key critical modules in the electrolyzers that deal with the specific device that divides the molecule. As you know, in the electrolyzer, you insert electricity, water, you break the molecule, and you get hydrogen. The separator, that's a key component that the competition is happening in the that are focusing mostly on the variety of channels that they use for making the separation. So in a nutshell, the device that separates the molecule is the one where most of the competition is happening. Now,
so let me understand this, Julio. Let me understand this. So electrolyzer is sort of a production of hydrogen mechanism, is it?
Correct.
And so, so is it using electricity?
Yes. So right now, as many people know, there are companies that, for example, have already designed and they already selling cars that run on hydrogen. If you go to California, you can actually get your Toyota car into a hydrogen charging station. But what most people miss is that most of the hydrogen that right now is being delivered comes from petrochemical plants. So the H comes from the hydrocarbon, right? So they are getting hydrogen from hydrocarbons. So in order to make the hydrogen industry to be really a contributor to the green industry, we have to develop not only efficient but cost-effective machines that will generate the hydrogen without the hydrocarbons. So the electrolyzers are the machines that decouple the water into hydrogen. Now, as you have just remarked, the input is electricity. So when what we call green hydrogen, the green comes from green electricity. So if the electricity that you provide to the electrolyzer comes from renewable sources like wind, solar, and others, then you are getting green hydrogen. Okay, so I think that explains in a succinct way
Yes.
what. Oh,
You dropped off for a
oh,
minute. So I was
okay,
going to ask you. So I understand that. So we have electricity sources like solar and wind. That
right,
if you use that electricity, you can produce hydrogen. Now, hydrogen is useful, I guess, for transportation, like in automobiles that you mentioned, but also in modalities where you can't really have solar and wind. So, in closed spaces or very critical areas. So
right,
hydrogen then is sort of a conversion mechanism, is it? I mean, so the green
yes,
energy is already there, and hydrogen is a way to store it in some ways,
right,
right?
right. So let me build on that. The way I see hydrogen is basically a substance or a means by which we will be able to transport stored energy. Okay, so let's say you go to a place, I don't know, a desert in Peru or Chile, where there is a lot of sun, radiation, and you use that to generate hydrogen, right? So the advantage would be, or an opportunity for hydrogen relies on three areas. One is that we package the hydrogen and we transport hydrogen from one continent to another in a way similar in which we transport now hydrocarbons. The engineering technology to design and build tankers that will allow the transportation of hydrogen is in many ways similar to the LNG tankers. Okay, so we have I mean, human beings, we have the know-how to design and build the means of transporting hydrogen as a mean to send energy from one place to another. Now, Europe has already put together a very thorough study, I mean, the European Union, about what would be the industries in which hydrogen will have the most potential. And they are two. One is ships, boats, I mean, to power ships and to power airplanes. Those are the two. However, de facto, we already have three companies, one in Japan and two in, I think it's a Mirata is the name of the model of the Toyota, and two in Europe, where de facto we already have cars that can operate on hydrogen, right? If somebody asked me what would be a good strategic decision for countries that want to get into the hydrogen industry, I would tell them, since we know that by default the renewable have up and downs, it depends on how much wind and sun is available. Try to invest a lot of your R&D on how you can store and transport the hydrogen. because I think that's the best and most pragmatic opportunity for hydrogen. I hope I have addressed your question.
Yeah, so that makes a lot of sense. So, one issue with green energy, solar and wind and geothermal included,
Right.
is that it is almost when they produce energy, they're producing a lot of energy. And so, along with that, storage has always become an issue.
Right.
And locally, use something like pump storage or something like that to pump water up and then bring it down
Right.
to be converted. So, hydrogen seems like a more efficient way to
Yes.
store electricity, and with the added advantage of, as you mentioned, of transportation. So you can actually move it from X to Y and
Right.
utilize it. So what is sort of the efficiency factors we see? So when you convert electricity, 1 unit of electricity into hydrogen and back into some production,
Yes.
how much
Yes.
how
Yes.
much do we lose in that
Yeah.
process?
Excellent question. So I will speak in the simplest possible terms, right? If one country uh, requires 100 units of energy to run its electricity grid, okay, that country would need twice as much electricity to generate hydrogen, okay. So you say, oh, Julio, then it doesn't make sense. Why would we generate if we need twice as much electricity? It doesn't make sense, but it makes a lot of sense if you think about hydrogen again as a means for storing and transporting that. Right now, strategically, many countries evaluate their performance on electricity generation with a term that more or less sounds like this. We can generate enough electricity for our national demand. So we don't need to generate more, right? So they don't go into putting together more dams or more hydroelectric because they say, oh, we already have for our consumption, right? But if you change your mindset and you say, wait, so we are not generating more electricity because we have enough for our national consumption. But wait, you can actually start exporting energy in the way of the hydrogen, right? So from that perspective, it makes a lot more sense. Now, the second part of the answer is you have the electrolyzer, which is the machine by which you generate hydrogen. But then in your car, you will need a fuel cell, which is the opposite, right? Where you enter hydrogen and then you generate electricity, right? I don't have the numbers on top of my mind, but that's a very efficient machine. I mean, compared with other systems, right? Plus, the challenge, Elon Musk will disagree with me immensely, but that's fine. He will say, oh, no, it doesn't make sense. But in reality, the batteries, every technology has its pros and cons, right? So batteries for electric cars are already presenting the huge challenge of the lithium, right? So they are already looking into Bolivia, Chile, and Argentina as the triangle of lithium triangle, right? Because they will need huge amounts of lithium for the batteries for the storage. But for storing hydrogen, all you need is a well-designed small pressure vessel. That's all you need, right? So you put the energy in the pressure vessel, and then you have that sent to your fuel cell that then give you the electricity that will power your electric motors for your electric car. So in reality, when they talk about hydrogen cars, they need to understand that in reality, the car is electric, it's running on electricity, but you are using the hydrogen as the initial source of accumulated energy that then you move from, let's say, the chemical energy domain into the electrochemical domain in a fuel cell, and then finally you are in the only electric domain. So there are three transformers. Okay, I hope this is helping.
Yeah. So let me understand this a little better, Julio. So fuel cell, as you say, is a mechanism by which we can convert hydrogen into electricity. And so in an automobile that uses fuel cell, hydrogen is supplied to the fuel cell through some mechanism, right?
It's right. So you from the hose in the pump station, you fill a tank with hydrogen. That's your fuel. The fuel feeds the fuel cell, and the output of the fuel cell is electricity that goes into your electric motor. Or you can also store in a little battery if you want. Mm-hmm.
So what is the sort of safety aspects of this, Julio? You know, hydrogen loves oxygen, and when you have a hydrogen tank, is that safe?
Right. So it is safe as long as you design and build the pressure vessel inside which you store the hydrogen. In my personal, humble, professional opinion, is the most critical module related to safety in a car. Okay, because if something could go wrong, it will be on the pressure vessel. Keeping in mind, I bet most people have seen this in YouTube videos, the flame generated by a hydrogen fire, you don't see it. You know, it's not like when you put fire on gasoline, you see the flame. When you have the flame in hydrogen, it is not the same. So so you don't want that, right? Yeah. So the short answer to your question, Jill, is the key technology or the key know-how to make the hydrogen cars safe is, in my opinion, in the design and manufacturing of the pressure vessels. Now, we have to add a very important component. You also want the car to be light, right? You don't want to build a pressure vessel that is, I don't know, like King Kong, very big, right? So then you have to go into composites, right? So another branch of technology that comes in the car is the composites technology, which is also, at least here in the United States, it's very well, it has very good codes and standards. So you have the codes and standard from some engineering organizations that deal with pressure vessels, and then you also have the same for the composites. Mm-hmm.
So just for my own understanding, so you said the fuel cell is very efficient machine to convert hydrogen back into electricity. What is sort of the efficiency factor there? Is above 80%?
I don't have that on top of my mind.
Okay.
Yeah. But for sure, it's a lot more efficient than an internal combustion engine. You know, an internal combustion engine, I think, is like 35 at most, right? So yeah.
So the round trip, let's say the fuel cell efficiency is 75%. The round trip is 50% lost in conversion to hydrogen, and then an additional 25% lost in converting back into electricity. It is still probably pretty good, pretty high efficiency, right, compared to alternatives in transportation.
Oh, yes. However, so yes, for the cars, but let's take a couple of steps back and let's go back to the note I made about the European Union, right? So they are already, for obvious reasons, or I think 60 to 70% of the energy generated in the European Union right now comes from hydrocarbons. They don't have hydrocarbons, right? So they bring it from many different places. So they've been looking at strategically, if they got into hydrogen, what would be the best strategic decision? And remember, there are several papers about this. I can share that with you later. I can also share with you a couple of keynotes I have given about this, where basically they're saying ships, right? So for maritime transportation and airplanes. Can you imagine at some point in the near future not using hydrocarbons for maritime transportation and not using hydrocarbons for airplanes, that would be great. Now, I am not saying that I am looking into a future where we don't use hydrocarbons, because people who are not engineers may not understand that hydrocarbons are essential for our civilization, right? Like almost everything that surrounds us has some form of polymers, and they come from the hydrocarbon, right? So maybe reducing the use of hydrocarbons for energy generation or consumption and focusing their use for materials is something that will help us a lot. Plus, obviously, at some point in the near future, we will be able to figure out how to do the CO2 sequestration, and I think that will have a really impactful effect on our solution of the global warming.
So, what is the competition to hydrogen for storage and transportation?
Right now, hydrocarbons. There is no other.
So there is no real alternative. I mean, we can store electricity in multiple ways if it is local, but if you need to transport it, it appears that there isn't any alternative.
Right. So right now, in the simplest possible terms, if you generate electricity from green sources, you need some sort of batteries to store it. There are some efforts with very good early results about storing thermal energy in materials like sand. I think Norway is the one that has succeeded first on doing this, right? But see, most of the efforts are about, okay, how do we deal with the peaks and valleys of green energy generation so we can store the peaks, so we can use in the moments of higher demand, right? But there isn't yet a way besides transporting batteries that are very expensive and they are prone to fire. There is nothing else yet, right? So that's why I think hydrogen is a good candidate for doing this.
Yeah, so if you're successful in fusion, I don't know where we are. There have been some noise around it. France appears to invest a lot into it. If you're successful in fusion, and we do get sort of free energy, so to speak, then the focus really shifts to storage and transportation. And the current state of batteries, I don't know much about this, Julio, but the current state of batteries doesn't appear to be there at scale, right, for storage?
No, besides cars or buses, no, right. There is a lot of research about that, but unless you go, I like to use the word intergalactic, unless you go into an intergalactic super capacitor, there are not many ways to do that, right? Now, there are companies that have already been using fuel cells at large scale, mostly companies that deal with servers. Like, I don't know, don't call me on the company, but companies like Google, Amazon, they have already been deploying fuel cells, but mostly to deal with, let's say there is a drop in the energy that their server centers require. So they have the fuel cell next to the center, so it can secure that they will always have a source of energy. Now, there is, I did a very thorough investigation about how mature these alternative solutions were for the use in the oil and gas field operations. So when you are exploring, looking for oil and gas, or you're already extracting, producing, or so on, during the whole process, the operations by the field, so next to where the wells are, they require electricity. So what they do right now is they are using diesel electric generators, right? So they are using hydrocarbon, right? So I know for a fact that there are companies that are very interested on switching from diesel electric generators into other sources. And I have already done the study about how mature technologies are for doing that. And the key factor that I used was uh, ballpark, what is the cost per kilowatt hour, so energy, that they can get from hydrocarbons by the field, right? Versus cost per kilowatt hour with a fuel cell or some other sources. There are companies that are trying to use modifying some other like methane and other sources, so they can use the exact same diesel engine, but they have some devices that allow to use, instead of diesel, to use other, let's say, biofuels, right? So
Yeah, so you have another topic area here. I don't know anything about this, Julio. So you say off-grid thermal without
yeah,
PVC, which is photovoltaic cells, I
yes,
would imagine, or
right,
wind,
yeah,
and with rocks only, you say. But what does that
yes,
mean?
yeah. So in a very interesting project in which I have been involved in South America, um, I got to learn that every winter, so right now, which the winter is starting there, above 4,000 meters above sea level, the temperature in Celsius during the winter can drop below or -5 Celsius. During the day, they could probably be up to 12 or 13 Celsius. But at night, the houses off grid, because they're in those isolated areas, they don't have gas, they don't have electricity, they don't have windmills, and they don't have solar. So that presented our team with a very interesting question. I mean, could there be a system that provides them with thermal energy uh, uh, without any other means, so not even photovoltaic? And why not photovoltaic? Because if you have photovoltaic, again, you go back to, you need to store it. And then many of these people, they don't have the means to pay for covering the roof with photovoltaic, and even less to have intergalactic batteries. So we designed a system that has a box that is pretty much a mini greenhouse. It has a transparent plate, it has a black body, and below that, you are running air. And the radiation at these very high altitudes is very high. It could be about 700 watts per square meter, which is very high, and it's very bad for the skin. So we convert that into thermal energy, and then during the day, when there is sunlight, we are running this with a very small fan, like the size of the fan of the old desktops. So we run that warm air through a box that is about half by half by half square cubic meter, sorry, um, full of rocks, which are about the size of regular potatoes. And then the air runs through these rocks. During the day, we have been able to reach an average of 70 Celsius when outside was very cold. So now the rocks become the capacitor. The system is called CAT, C-A-T, C for collector, that is, as I told you, A for accumulator, because we accumulate the thermal energy in these rocks. And then T is the transformer, which is the house. So at night, we close the loop between the collector and the accumulator, and we open a loop between the accumulator and the house. So we run the cold air from the house through the rocks, and then we reinsert that into the house. And to be very simple terms, we have been able to keep it at 17 Celsius constant during the whole night, while outside was -3, -5. Bless you. And this is a very good result, because it's giving you about 20 Celsius of difference, right? And everything is running off grid. And I am right now, like literally now, working on a system that is also aiming to use geothermal. But I can talk about that after you tell me that we have covered your question about this question that you asked me.
Yeah, so the rocks, using the rocks that are locally available,
Yes.
And the reason is it's locally available, so you don't
Yes.
have good investment. But
Right.
Presumably there are materials that are better at it, right?
Yes. Yes.
And so yeah, there could be products that are much more efficient in this.
Correct, 100%. But the design philosophy was, what is the best we could do with what is available in the surrounding, right?
Yeah.
So when we came up with this idea with my colleague Bill Warwick, who has worked all his life on heat transfer and mass transfer, he was coming up with very, very good ideas. But then I said, hey, let's push ourselves further. There isn't any intergalactic material to store the energy, right? And then he asked a very interesting question. Do they have rocks? And I told him, of course, there's abundant. So I said, okay, we have the solution because it has a very good capacity to store energy. In fact, there are countries where people heat rocks, they put underground and they put the meat inside, they close it, and that's how they cook. So that's through many different human societies, right? So, but
Yeah,
yes, we could come up with better materials. Yeah.
Yeah, that's what I was thinking, Julio. So tropical countries, which gets very hot,
yes,
and fuel is very scarce. So it seems like this could be an approach to cooking potentially in tropical, third world areas.
That could also, yes. Now the rocks, we have had different designs for the accumulator. Initially, would put the accumulator at a certain distance from the house, the collector at a certain distance from the house, but the intuition or the engineering intuition tells you, hey, minimize the distance between all the components, so the pipes that run between them, the more surface you present to the environment, then the easier will be for the heat to escape, right? So we have minimized everything now. The collector is almost exactly on top of the accumulator, and the accumulator is basically glued to the house, and with that we have increased the efficiency. If you want, we can talk a little bit about geothermal. Just let me know.
Yeah. So I was just wondering, can we run this in reverse? Meaning, if you have cold flow, can the rock store cold
Yes.
and then bring it back?
Yes, you could. Yes, you can inverse. You can inverse the process. Yeah, the rocks are almost equally efficiently on both, right? So
right.
Yes.
Yeah, that's really interesting. So yeah, we want to talk a little bit about geothermal. There is increased interest in this area, especially in the northeast of the US here.
Right.
I see a lot of companies offering geothermal energy. So before we get into the details, how exactly does geothermal work?
Yes. So in general, the deeper you go underground, you will get in the winter more temperature underground than the temperature above ground. Okay, that's the basic concept, right? So if above ground, let's say you are at 20 Celsius, below ground, in the winter, it will be warmer. So let's say let's make it even simpler, okay? Let's say 5 Celsius during the winter outside. Underground, you could be, depending on how deep you go, you could be at 20 or 30 Celsius. So that delta temperature is the basic concept for getting thermal energy to heat places, right? So all you need to do is you run a pipe with a thermal fluid that goes from the surface down to the source of thermal energy underground, you get that thermal fluid heat, warm, and then you send that fluid, and now it's warmer than it was on the surface, and you send it back up to the surface, and now that is warmer, and then you can use that, for example, with a heat pump. And now, okay, so I will go into the heat pump in a few seconds. Now let's reverse this. In the summer, let's say on the surface it's 30 Celsius, right? Very hot, muy caliente. But now down underground, you will be at 25, so it's colder. So you can send now the warm fluid from the surface down to, let's call it a heat sink. Now the underground is a heat sink, right? So you cool down the fluid that was coming at 30 Celsius, and you put that in interaction with the underground, which is at 25, so you can cool it out, right? Cool it off, and then you send it back. So use that fluid. You can use the same, exactly the same process to cool down, right? Now, the heat pumps present a very nice advantage because the heat pumps can be reversed winter and summer. So just 2 days ago, I filed another provisional patent where I am talking about using this not as the main source for thermal energy, but in my opinion, is a source of energy to complement the consumption of electricity. So let's say if a person has to invest $1,000 for the 5 months of winter in the northeast of the United States, I'm using $1,000 just as a reference, right?
Yeah.
So if we could use geothermal to reduce the delta temperature, then, I mean, the delta temperature against which you have to fight to heat the house, right? Then your bill could go down by, let's say, 30%, right? So now you don't pay 1,000, but you pay 700, right? So in my opinion, the opportunity for geothermal for residential is not having geothermal as a source of thermal energy for the whole house. It's just to complement the electricity. So you will continue using electricity or gas, whatever you use, but you can complement with the use of the energy underground. You can reverse that, right? Now, the key challenge, why it has not become widely used, is because the current approach is to dig, well, you don't dig, you perforate a well, which is 200 feet at least, so at least 70 meters deep, right? And that is very cumbersome. I mean, you live in New England, as I do, so the houses are relatively small, and the yards around the houses too. So you have to come with literally a derrick, and then you have to drill 70 meters, and you basically destroy the yard, right? So it will take, I don't know, 6 months it takes tens of thousands of dollars to make that happen. There is an alternative, which is to do trenching. So it's even worse, right? So you just make trenches and then you lay the pipes horizontally, right? So yeah, so please go ahead with the next question related to this.
Yeah, so there is always, there's an efficiency question. So when you go deep, say 70 meters, there
Yes,
is a pump involved in the
correct.
circulation. There is electricity
Yes,
involved in the circulation. So the ultimate question is, what's the net effect of it, right?
right,
So if the 5
right.
degree, 10 degree differential, will
Yeah,
that be sufficient?
yeah. So I will answer with the time it takes to break even. Okay, it's more or less 5 years. Okay, so all the investment that you make, so let's say you invest about $30,000, so in 5 years, 6 years, so you will pay it, right? So it's about $6,000 that you can save, right?
The
And
difference, yeah.
then, right, that's the way I approach it. But again, the challenge is how expensive it is to deploy, right? How to make it happen. So I am very focused right now. I have done a lot of analysis that has rendered very promising results, that instead of going deep 70 meters, you could do several shallow multilateral. So you go only 3 meters, and then you do several horizontal. Let's say for discussion purposes, 8 horizontals of 12 meters each, which is very manageable under a house, could give you about the same amount of thermal energy that you will get from 70 meters deep without all the disruption. Mhm.
So is the differential going down, temperature differential sort of linear?
Yeah, so you mean how the delta temperature increases as you go down? Yes.
Yeah.
I don't remember the number, but after about 5 meters, okay, the gradient is very predictable. Okay, so let's say, just for discussion purposes, right, it's about, let's say, 1/10 of a degree per foot, right? So 10 feet will give you, or 1/10 of a degree per meter or per foot, I don't remember, but it's very, the gradient is very predictable and uniform by latitude and longitude. In fact, one could predict with some decent level of accuracy. You look at the map of United States or North America, and you can pretty much predict what will be the delta that you will get for 70 meters or even for 3 meters. Yeah, it's very predictable. Yeah. Now, most of the efforts of the government right now, so I've been looking at all the requests for proposals from the RPI and DOE, in particular in the last 6 to 7 months since the current administration got the approval of the big funding last year. Remember, it's like $0.7 trillion and a significant part for renewables. So a lot of the requests for proposals are related to geothermal, but almost all of them aim for the big, how do they call it, the big kahuna, right? So like a huge reservoir that you drill deep quickly, and then basically you get a very large source of thermal energy that you can use to feed many houses, right? That's a valid approach. I think that for residential, the approach may have to be, there is an additional approach, which is the one I'm talking about.
Yeah, I mean, centralizing energy production always have to take into transmission efficiency and
Right.
all of that as well, right? So
Right.
it's
Right.
a complex question. So in conclusion, Julio, so in the
Yeah.
energy area, if you look forward, so sort of look at all the alternatives that we talked about, PVC, wind,
Solar,
hydrogen
wind,
is more
yes.
for transportation, hydroelectric. Hopefully, the hydrocarbon-based energy production is going away. So green energy, let's say green energy alternatives are going to dominate in the future. How do
For
you
sure.
see
For
this
sure.
panning out? Without knowing a lot about it, my thinking is that if you look at efficiency, these technologies are going to sort of parade themselves on the efficiency scale, and one of them is going to be better than the others.
Right.
Then the policy question is, if one is better than the others, why are we worried about the others?
Yes.
So 2 questions. Do we know what is dominant? And number 2, from a policy perspective, why are we heading in a lot of different directions, it appears?
Right. So I will give you my opinion, right? My professional opinion. I don't think the solution to that challenge that global warming is presenting us with, the solution doesn't rely on one way of renewable. I think that is all of them have to go together. solar, wind, geothermal, you name it. I would advocate for the rebirth of nuclear. Okay, many people say, Julio, that's not good, nuclear is bad. I respectfully disagree. I think nuclear is a very important player to solve this challenge. Okay, now, why all of them? Because with the technology knowledge that we have right now, I mean, as a human race, I don't think anybody can say or bet that one will be the solution, okay, will be complementary. Now, I will go to the hydrocarbon industry for 1 second, okay? So I worked in the oil and gas industry for more than 13 years in product development and research. The end of the hydrocarbons, the mythological expression, the end of hydrocarbons, is not that we will run out of hydrocarbons. I mean to be funny with this. When we, as a human race, we finished or we stopped, we got off the stone age, it's not because we ran out of stones. The stones are still around, but we found other technologies that were better than the stones, right? So in the case of the hydrocarbons, I think the end of the hydrocarbons is not that we will run out of hydrocarbons, but the cost or the price that we are willing to pay to get the hydrocarbon from underground, it will be something that we may not want to pay $200 per barrel, period, right? So that's what will stop or end the hydrocarbon age, right? So in that situation, I don't think we will have only wind or only solar. We will have to have a combination of them. So yes, addressing all of this, you and I are engineers, we tend to say, let's if the modules of the system are in series, let's multiply the efficiency of each one of them, and we will get the efficiency of the whole system, right? Yes, that's valid. But in the absence of hydrocarbon as a viable financial solution, I think having the other one, so it will not be just about efficiency, it will be that they will be the only ones that will be viable or available. I hope I have addressed your question in a clear way from my perspective, which is not just about the financial aspect, sorry, it's not just about the efficiency factor, but it's about that hydrocarbon may not be viable because it will be too expensive, right? So we will need the other ones. Please ask me another question if you think I was not clear.
No. I mean, there are. It's still complex. So solar, it's not just PVC. There's concentrating solar that could be at scale. Nuclear Lockheed engineers recently did a micro nuclear generator that would be in the basement of a building. So there are a lot of things going on, and I always felt that there must be a way to rate them. So given a dozen alternatives in the green arena, there has to be some sort of ultimately comes down to finance, which is what is the total cost of production of a unit of energy, right? And all these technologies provide different numbers of that.
Yeah. So I will attempt an answer. So I've been thinking about that. It is not non-dimensional, it's dimensional factor. But the one I will use is dollars per kilowatt hour by the electric outlet or by your heating pipe, right? So I will rank all of them by their dollars per kilowatt hour of energy. It's tricky because, as you remember, when I was talking about the Miata car, I was talking about moving from chemical energy domain to electrochemical energy domain to electric energy domain. So it's tricky. But we can work it out, right? So you have dollars per kilowatt hour. So that's one way to compute. But, and there are several very interesting papers I have read about this, which is the technology, Jill, that will solve our problems by 2050, has to be by 2050, does not exist right now.
Yeah.
Okay, so every person who has a decent sized coconut, and this is the coconut, will tell you that actually we are on our way to develop that technology that will integrate several, but we don't know yet. Okay, it's like in 1970, somebody predicted that we were going to reach the peak of oil and hydrocarbons like in 20 years. But that prediction, and I will go back to our question in a few seconds, that prediction was based on the technology that was available in 1970. So we didn't have the personal computer, we didn't have the computer power and so on. We didn't have robotics. So a lot of what moved in time, the peak of the oil and gas has been all this technology. You know, I work in R&D for so many years. We use robotics, we use computer, we so many things, right? So we are in a revolution right now of technology that by something will happen between now and 2050 that doesn't look exactly as anything that we are dealing with right now. I think it will be an integration of this. And I want to add one point. Materials or material science is a key component of all of this. You need hydrocarbons to make the windmills. You know, the windmills are not made out of metal. They have things that are made with derivative from hydrocarbons, right? The PVC, the photovoltaic cells also use hydrocarbons. The fuel cells, not too much, right? But the point I want to make is hydrocarbons will be part of the solution, right? So to summarize, so one factor is dollars per kilowatt hour. The other factor is the evolution of technology between now and 2050. So we have to assess, and we can predict how the price of dollar per kilowatt will change versus time. And the third factor is the evolution of the materials science between now and 2050. I think those are the three factors, right? Dollars per kilowatt, technology evolution per year between now and 2050. And the third one is a key enabler, which is the materials, right? And maybe fourth will be a social, a political science guy will tell you, and I agree with you with them in great part. It also has to do with the policy makers, right? Because if there is not a stimulus packages to stimulate the development of these solutions, at least in the United States, we are gonna be eaten alive by the other two sides, you know, on the other side of the Atlantic and the other side of the Pacific. You understand what I mean? Yeah.
Yeah, there's another dimension. So I'll just conclude on this, Julio, to get your perspective. So another dimension that is the world population is plateauing. And if we look forward to 2050, we might already hit a point where the population starts to decline, the overall population in the world.
Yes. Right.
And so it's almost like if we survive till 2050, the problem might just go away because there cannot be enough
maybe
to consume energy.
Yeah. Yes. Yeah, so there are many things that could happen, right. But I think we have to keep an eye on the price of the hydrocarbons, because I think the price, I mean the barrel, right, as soon, so let's start paying attention when it starts to go above 110. Let's not panic, but I think that's a good index that tell us that either we are having more mature pragmatic solutions with the alternative link energies or something really ugly is going to start happening. Yeah.
Excellent. Yeah, this has been great, Julio. Thanks so much for spending time with me.
Same here. Thank you very much for your time. Could we stay offline for 1 minute after you
Sure.
finish this? Yeah.
Sure.